Welcome to this explainer. Today, we're going to do something pretty incredible. We are going to zoom all the way down from a macroscopic steel bolt, the kind you might just hold in your hand, to the very atoms that make it up, uncovering the hidden structures of metal. It's a fascinating journey into the microscopic architecture that literally makes our modern world possible. Okay, here's our structural blueprint for today. First, understanding metal crystal structures. Second, ferrite, body-centered cubic. Third, austenite, face-centered cubic. Then the 41% secret, and finally, why this empty space matters. We're going to compare two distinct crystal structures and build up to a massive twist. Part 1. Understanding metal crystal structures, the invisible building blocks of steel. To really grasp metallurgy, especially if you're gearing up for your certification exams, we first have to picture how these structures exist in 3 dimensions. I want you to imagine atoms acting like ping pong balls, stacking together to form perfect microscopic cubes. Establishing these acronyms right off the bat clears the path for us. BCC stands for body-centered cubic, and FCC stands for face-centered cubic. These are the 2 fundamental geometric patterns iron atoms form when they bond together. Part 2. Ferrite, body-centered cubic. The tightly packed center. Let's start building our first atomic model, ferrite, using that BCC blueprint. Just picture a standard cube in your head. To build this out of our atomic ping pong balls, you place a ball at all 8 corners of the cube. So 4 on the top, 4 on the bottom. Simple enough, right? Then, for the second step, you wedge a single ping pong ball straight into the center. Because of how it's positioned, the absolute core of the cube is completely filled up. So the crucial takeaway here is that ferrite, known as the BCC structure, uses a total of exactly 9 atoms, 8 on the outside corners and 1 right in the middle. Because of that specific layout, it leaves absolutely 0 empty space in the middle of its cube. The center is fully occupied and incredibly dense.
Part 3. Austenite, face-centered cubic, the structural shift.
Now let's completely shift gears and look at our second model, austenite. This one uses the FCC structure, and it acts very differently. Check out this contrast. Ferrite uses 9 total atoms, and its center is solidly filled. But austenite? It jumps all the way up to 14 total atoms. Its faces are filled, but, and here's the wild part, even with those extra atoms, austenite's center is actually entirely vacant.
Let's physically picture how this actually works. To mentally build austenite, you put atoms on the 8 corners, just like we did before, but then you slap 1 ping pong ball onto the flat center of all 6 faces of the cube. Top, bottom, left, right, front, and back. That gives us our 14 atoms total. But because those 6 atoms are resting directly on the outer faces, the absolute core of the cube remains completely hollow. Now this presents a real puzzle when you first think about it. How on earth can a structure with more tightly packed ping pong balls on the outside, 14 of them, compared to just 9, actually have a giant void right on the inside? Which leads us to part 4, the 41% secret, measuring the missing space. This perfectly answers the great missing center mystery, and it reveals a number you absolutely must memorize: 41%. Due to the geometric layout of those FCC faces, the austenite structure actually consists of exactly 41% pure empty space. And hey, you don't just have to take my word for it. The instructor in our source material notes that you can actually prove this. If you physically glue together this FCC model out of ping pong balls, keeping that center empty, and drop it into a water tank, you can measure the results yourself. The water displacement definitively proves this massive 41% void exists right in the middle of the structure. It's not just theory. It is a mathematical and physical reality. Finally, part 5, why this empty space matters. The key to metallurgy. Let's see how this all builds into real-world applications. Take a look at this quote right from the source material. This is perhaps the most core element to understanding the austenite ferrite steel structures. I mean, that directly validates why we just spent time building these models in our heads. This void isn't just some quirk of geometry. It is literally the master key to understanding your exams and mastering real-world engineering. So here's the so what. That empty 41% space in the center of the austenite structure is exactly where other elements, like carbon, can hide out when steel is heated up. When the metal shifts into this FCC structure, that giant microscopic void opens up, acting almost like a sponge. This empty space is precisely what allows us to manipulate steel, give it different heat treatments, and harden the metal to build the super strong structures we rely on every single day. As we wrap up this explainer today, I want you to ask yourself, how are you going to use the knowledge of this 41% empty space to master the complex heat treatments of steel in your next certification module? How does knowing about this brilliant microscopic reality, a giant void inside a crowded cube of atoms, change the way you look at every piece of steel around you? It's honestly incredible to think that the strength of the metal holding up our buildings relies so heavily on, well, completely empty space. Thanks so much for exploring the microscopic world with me today.